In this video, I'd like to present our work evaluating replay techniques for asynchronous task handover in immersive analytics. This research was conducted at Georgia Tech IVI Lab and University of Waterloo. Collaboration in immersive analytics is often categorized as either synchronous or asynchronous. For asynchronous collaboration, in which users work on the same project at different times, real-world analytical workflow often involve a handover process. An incoming analyst must pick up where a predecessor left off. Currently, this handover relies on traditional methods like chat logs, meeting notes, or static 2D annotations. However, these methods fail to capture the rich, embodied interactions and the dynamic spatial context that are inherent to immersive environment. To bridge this gap, we propose using session replay to allow successors to re-experience the predecessor's analytical journey. It's been proven that immersive replay can serve as a powerful tool for asynchronous tasks, such as virtual guided tours. However, immersive analytics presents unique challenges, including the need for users to perceive rich visual details and understand the collaborator's insight-forming process. Therefore, we aim to investigate the effectiveness and key design trade-offs for using replay for immersive analytics task handover. Based on prior literature, we investigated three key variables: the viewing platform, perspective, and navigation control. This factorial design resulted in 8 possible conditions, from which we excluded the technically redundant first-person active condition, as first-person view is inherently passive. The evaluation followed a two-phase plan. Phase 1 was a comparison within each platform to identify the optimal configuration for PC and VR respectively. Phase 2 then compared these two optimized media against each other to determine the most effective replay settings for task handover. Each session followed a structured exploratory analysis process, which the participants were asked to reproduce to test their memory of the workflow. Also, a comprehension questionnaire was created for each task to evaluate the participants' understanding of data insight, workflow details, and the analyst's intent. In Study 1, 24 participants were randomly split into PC and VR group. Each group experienced the following 3 different conditions for comparing perspective and navigation control. First-person passive, a first-person view from the original analyst's perspective with no user control. Third-person passive, a third-person view that followed the analyst's avatar along a predefined camera path. Third-person active, a third-person view that gave the viewer full navigation freedom to move around the scene. During the study, participants went through 3 different tasks after training session, each followed by the workflow construction and comprehension test. The order of the dataset and conditions were counterbalanced using orthogonal Latin square. The results showed that for VR, the third-person active condition gave the best performance in both task understanding and workflow reconstruction, and 58% of participants preferred this condition. This indicates the need for navigational agency in VR. For PC, the first-person perspective passive condition performed the best because it's guiding users' visual focus, while third-person perspective active condition performed the worst, as keyboard control might introduce extra cognitive load for users. Based on these findings, we conducted Study 2 to compare the best settings of PC and VR group. For the PC, since first-person and third-person passive condition yielded comparable performance, we developed a novel hybrid first-person, third-person format that combined the guided detail of first-person with the context of third-person. We directly compared this optimized PC hybrid condition against the optimized VR third-person active setting. We also added new features based on user feedback, including proximity-based avatar fade-out, PC perspective switch, pause, and rewind. To evaluate user interaction using the new features, we also recorded user behavioral data and interaction events. Study 2 adopted a procedure similar to Study 1. We increased the task difficulty and extended the replay length for clearer comparisons. Results from the statistical analysis showed VR-optimized conditions significantly outperformed PC on multiple measures, including analyst intent comprehension, insight understanding, and workflow reconstruction. It also leads to higher user satisfaction and lower frustration, though with greater physical demand. Moving to our discussion, we observed a distinct platform-based preference. Agency is the priority in VR, while a guided view is essential for PC. In VR, users leverage embodied agency to laterally move around the space, which helps them navigate the visual details and better understand the workflow. Conversely, the PC's limited field of view associates a guided perspective to check details, and active navigation using keyboard introduces mental workload. Study 2 shows that, for understanding complex analytical processes, the benefits of embodied agency outweigh a guided view. While guidance helps track actions, agency fosters the active sense-making required to truly reconstruct a predecessor's intent. From our discussion, we frame session replay as an active sense-making tool rather than a passive video. By integrating temporal control and perspective switching, users move beyond simple observation. From the interaction data, we observed that users naturally use the timeline features to offload temporal demands. We also observed users form their own comprehension strategies. For example, going over the entire replay for an overview, then relocate to key analytical steps for detailed understanding. Our study concludes with 3 actionable guidelines for immersive analytics replay systems. First, it's crucial to understand platform-based divergence and match navigation to the medium. Second, visual clarity should be prioritized considering the rich visual details in immersive analytics tasks. This includes using proximity-based avatar fading and highlighting the visual representations interacted with. Third, such replay systems should facilitate the active sense-making process by providing temporal interaction and annotation features. While our system offered primary insights on immersive analytics replay for task handover, future systems could benefit from refined annotation features, such as highlights and audio, to explicitly communicate insights. Also, new spatial temporal navigation methods could be leveraged for increased efficiency. Furthermore, for long analytical sessions, the replay could benefit from automatic filtering and clipping using large language models or vision language model agents. To summarize, in this paper, we built and tested a prototype of replay system for immersive analytics task handover. Through a 2-phase study, we provided empirical knowledge of the trade-offs between different perspectives, navigation control, and platform for replaying immersive analytics processes. We also drew a set of practical design guidelines for future replay systems of this kind.